Our Sun, a familiar life-giving star, but what if it's a mere speck compared to the true giants of the cosmos? Today we journey to the realm of stellar behemoths, stars so vast and powerful they defy imagination. We often think of black holes as the ultimate cosmic terror. But what if the most terrifying objects aren't voids, but colossal, raging furnaces? Stars like Stephenson 218, so large they could swallow our solar system out to Saturn, or R13601, burning with the light of millions of suns. These aren't just big. They're terrifyingly powerful. Their sheer scale, blinding energy, violent winds and cataclysmic deaths reshape galaxies. Forget the abstract horror of a black hole's singularity. Prepare to confront the tangible, overwhelming power of the biggest stars ever found. Are they the true nightmares of the universe? Let's find out. The terrifying power of the biggest star ever found. When we talk about the biggest star, it's a term that can be surprisingly slippery. In our everyday experience, biggest usually means largest in physical size, the one that takes up the most space. And in the cosmos, there are stars that stretch this definition to almost absurd limits. But in the stellar realm, sheer volume isn't the only measure of might. Mass, the actual amount of stuff packed into a star, and luminosity, the raw energy it blasts out into the void, paint an equally, if not more, terrifying picture of power. So let's dissect what biggest truly means and meet some of the universe's most extreme record holders in each category. First, let's tackle the champions of sheer, unadulterated size, the stars with the largest known physical diameters. These are typically red supergiants or hypergiants, stars in the twilight of their lives, having exhausted the hydrogen fuel in their cores. In a desperate bid to survive, they've fused heavier elements, expanded their outer envelopes to truly mind-boggling proportions, and cooled on their surfaces, giving them their characteristic reddish hue. They are the cosmic blimps, vast but not necessarily the most massive. Deep within the Milky Way, nestled in the star cluster known as Stephenson 2, some 20,000 light-years away, resides a strong contender for the title of the largest known star by radius, Stephenson 218. This crimson behemoth is a red supergiant, and its estimated radius is a staggering 2,150 times that of our Sun. Let that number sink in. 2,150. If Stephenson 218 were to replace our Sun at the center of our solar system, its surface wouldn't just swallow Mercury, Venus, Earth and Mars. It would extend out past the orbit of Jupiter and even engulf Saturn. Our entire solar system, out to the ring giant, would be inside this single star. The terrifying implication here is one of cosmic engulfment. Imagine our familiar celestial neighborhood, the planets we know and study simply ceasing to exist, vaporized and assimilated into the tenuous, superheated outer layers of this monstrous star. The sheer volume it occupies is almost impossible to truly comprehend. You could line up over 2,000 of our suns side by side just to cross its diameter, while its membership in the Stephenson 2 cluster and its precise distance are still subjects of ongoing astronomical refinement, crucial for accurately calculating its true size. The current data points to a star of almost unimaginable proportions. The terror it inspires is one of overwhelming scale, a physical presence so vast it makes entire planetary systems seem like insignificant dust motes. The scale of Stephenson 218 is truly mind-boggling. Thousands of suns could fit across its diameter, making it an almost incomprehensible giant in the cosmic arena. As we pull back to view its immense scale against the backdrop of stars, the true enormity of this stellar behemoth becomes clear. Planets would dissolve into its stellar plasma, vanishing without a trace. For a long time, another red supergiant, UY Scuti, held the title of the largest known star. Located about 9,500 light-years away, its earlier estimates placed its radius at around 1,700 times that of our Sun, still large enough to swallow Jupiter's orbit. However, the universe is a dynamic place, and our understanding of it constantly evolves. More recent data, particularly from the Gaia Space Observatory, has led to a revised, somewhat smaller estimate for UY Scuti, perhaps closer to 755 solar radii. While still a colossal star, this highlights a crucial point. Measuring these distant giants is incredibly challenging. UY Scuti is also a variable star, meaning its brightness and likely its radius pulsates over a period of roughly 740 days. This inherent instability adds another layer to its terrifying nature. Imagine a star so large that its very surface heaves and breathes on a cosmic scale, its boundaries in constant flux. The terror here is not just its size, but its restless, unpredictable nature. Even at its revised size, it would comfortably engulf the inner solar system, including Mars. Our own Milky Way galaxy doesn't have a monopoly on stellar giants. In the Large Magellanic Cloud, a satellite galaxy orbiting our own Sun 160,000 light-years away, we find WOHG 64. This red supergiant is another contender for one of the largest stars known, with radius estimates around 1,540 solar radii, though some studies have suggested it could be even larger, perhaps up to 1,700 or even 2,000 times the Sun's radius. What makes WOHG 64 particularly intriguing and adds to its mystique is that it's enshrouded in a thick torus, a donut-shaped cloud of expelled gas and dust. This cosmic shroud, likely material ejected by the star itself, obscures our direct view, making precise measurements difficult. The terrifying aspect here is the hidden power, a colossal furnace veiled by its own cast-off skin. This dust isn't just a pretty nebula, it's the remnants of the star's own substance, violently shed into space. It speaks to the immense pressures and instabilities within these aging giants. The thought of such a massive object so far away in another galaxy, yet still detectable and clearly undergoing dramatic mass loss, is a stark reminder of the universe's violent capabilities. It's crucial to understand that when we talk about the surface of these radius giants, we're not talking about a solid boundary like Earth's. Red supergiants and hypergiants have incredibly tenuous extended atmospheres. Their outer layers are so diffuse that if you could somehow fly a spaceship into one, you might not even realize you'd crossed its visible edge for some time. But this isn't a gentle fog, it's a superheated plasma. Thousands of degrees hot, even at its coolest. The terror is deceptive. It's not a hard impact, but a gradual immersion into an increasingly hostile environment of unimaginable heat and scale. Understanding the sheer size and mass of these cosmic titans is one thing, but to truly grasp their terrifying power, we must explore how these characteristics manifest, the ways in which these stars actively and violently shape their environments and meet their cataclysmic ends. This isn't just about passive immensity, it's about active universe-altering force. We touched upon the horrifying scale of stars like Stephenson 218, so vast they could swallow our solar system out to Saturn. Let's visualize this more deeply. Imagine Earth, our vibrant blue marble, not just scorched, but utterly consumed. As the expanding photosphere of such a giant washes over our planet, the atmosphere would be stripped away in moments, oceans would boil into space, and the very rock beneath our feet would melt, then vaporize, becoming indistinguishable from the star's own incandescent plasma. There would be no cataclysmic impact, no dramatic explosion for Earth itself. Just a silent, inexorable assimilation into a stellar inferno thousands of times hotter than any fire we can conceive. Even our own sun, the mighty engine of our solar system, would be a mere morsel. It would spiral inwards, its structure torn apart by the supergiant's gravitational tides long before it reached what we might call a surface. It would be like a candle flame dropped into a blast furnace, its identity lost, its matter reprocessed within the behemoth. The terror here is the ultimate loss of place, the complete erasure of everything familiar, consumed by an entity whose outer layers are more voluminous than the orbits of most of our planets. While red supergiants are relatively cool on their surfaces, perhaps 3,500 Kelvin cooler than our Sun's 5,800 Kelvin, their sheer surface area means their total energy output, their luminosity, is still tens or hundreds of thousands of times that of our Sun. But the true champions of luminosity are the most massive stars, like R136A1. This stellar monster, though only about 30 times the Sun's radius, shines with the light of nearly 5 million suns. Its surface temperature blazes at over 50,000 Kelvin. The terrifying power here is one of pure, unrelenting, sterilizing energy. Imagine a planet orbiting such a star, even at a distance that would be considered habitable around a sun-like star. It would be a hellscape. The sheer intensity of light would be blinding. The surface temperature would be high enough to melt lead or even rock. The ultraviolet and X-ray radiation pouring from R13601 would shred complex molecules, making life as we know it utterly impossible. Any atmosphere would be blasted away. It's a constant, inescapable bombardment of energy that leaves no refuge. Consider the energy. R136A1 emits more energy in a few seconds than our Sun does in an entire year. If it were to replace our Sun, Earth wouldn't just be hot. It would be vaporized almost instantly. The sheer flux of photons would exert a physical pressure, a light-driven wind. This isn't just warmth, it's a destructive force, a continuous barrage of high-energy particles and radiation that can sterilize vast regions of space. The biggest and most massive stars are not serene static orbs. They are dynamic, violent, and often leaky. Many of them, particularly Wolf-Rayet stars like R13601 or hypergiants like UY Canis Majoris, are engaged in a constant struggle against their own immense gravity and radiation pressure. This battle results in some of the most powerful stellar winds in the universe. These aren't gentle breezes. They are torrents of superheated plasma, atoms, and even clumps of matter, ejected from the star at speeds of thousands of kilometers per second. While 136A1, for instance, is estimated to be losing mass at a rate tens of millions of times greater than our Sun's solar wind. Over its short lifetime, it will shed many times the Sun's entire mass back into space. UY Canis Majoris has created a complex asymmetric nebula around itself from multiple massive ejection events. This isn't just a slow evaporation, it's the star actively tearing itself apart, casting off vast quantities of its own substance. The terrifying power here is twofold. Firstly, the sheer violence of these outflows. Imagine being caught in a cosmic hurricane carrying material hotter than the Sun's surface, moving at a significant fraction of the speed of light. Secondly, the impact these winds have on their surroundings. They carve out vast bubbles in the interstellar medium, trigger or disrupt star formation in nearby gas clouds, and enrich the galaxy with heavy elements forged in their cores. These stars are not just passively existing, they are actively and violently reshaping their galactic neighborhoods. All stars die, but the biggest stars don't go gentle into that good night. Their end is the most spectacular and terrifying fireworks display the universe can offer, a supernova, or, for the truly colossal, a hypernova. After a few short million years of furious burning, a blink of an eye in cosmic terms, these giants exhaust their nuclear fuel. Gravity, always waiting, finally wins. The core collapses catastrophically. For stars like red supergiants, this core collapse triggers a Type II supernova. The infalling material rebounds off the newly formed ultra-dense neutron core, or a black hole if the progenitor is massive enough, sending a shockwave hurtling outwards through the star's bloated envelope. In a matter of hours, the star is obliterated in an explosion that can briefly outshine its entire host galaxy. The energy released is staggering, more than our Sun will produce in its entire 10 billion-year lifetime, unleashed in a fleeting moment. The terrifying power of a supernova is its sheer destructive reach. The blast wave of radiation and superheated material expands outwards at incredible speeds, sterilizing any nearby planetary systems. Lethal doses of gamma rays and X-rays precede the physical shockwave. If a sufficiently massive star were to go supernova within a few dozen light-years of Earth, it could potentially trigger mass extinctions or even strip away our atmosphere. These are not just distant light shows, they are events of galactic-scale consequence. And for the most massive stars like R13601, the end can be even more extreme. They might explode as a hypernova, an event hundreds of times more energetic than a typical supernova, potentially producing long-duration gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. These focused jets of energy, if aimed at Earth even from the thousands of light-years away, could have devastating consequences for life. Alternatively, some of these titans might collapse directly into a black hole with little or no visible explosion, silently vanishing from sight, their immense mass creating a new gravitational trap. We began by contrasting giant stars with black holes, but for the most massive stars, a black hole isn't a competitor, it's their destiny. stars significantly more massive than those that form neutron stars, perhaps those initially over 25 to 30 solar masses, and certainly behemoths like R136A1, will likely end their lives by collapsing directly into a black hole, or via a supernova that leaves a black hole remnant. The terrifying power here is the ultimate gravitational victory, all that mass, all that energy crushed down into a point of infinite density, warping space-time around it so severely that nothing can escape. So the biggest stars don't just possess terrifying power during their lives, their deaths give birth to another kind of cosmic terror. The very act of their demise can create the universe's ultimate traps. It's a cycle of extreme creation and extreme destruction, where the end of one colossal entity heralds the beginning of another, equally if differently terrifying phenomenon. The legacy of the biggest stars is often a black hole, a silent, invisible monster waiting to ensnare anything that ventures too close. The terrifying power of these colossal stars isn't just a static characteristic. It's intrinsically linked to their dramatic and surprisingly brief lives. Unlike their smaller, more sedate stellar cousins like our Sun, which can leisurely burn for billions of years, these giants live fast, die young, and leave an astonishingly violent cosmic corpse. Their life cycle is a race against their own immense gravity, a furious sprint of nuclear fusion that inevitably leads to a spectacular and terrifying end. All stars, big or small, are born from the same cosmic nurseries, vast, cold, dark clouds of interstellar gas and dust, primarily hydrogen and helium. Within these molecular clouds, denser regions begin to collapse under their own gravity. As the material clumps together, the core heats up. For a star to become one of the behemoths we're discussing, it needs an exceptionally large initial reservoir of material, a particularly dense and massive clump within that parent cloud. The process is a gravitational runaway. More mass means more gravity, which pulls in even more gas and dust, further increasing the mass and gravitational pull. Eventually, the core of this collapsing protostar becomes so hot and dense, millions of degrees, that nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing a tremendous amount of energy. This outward radiation pressure pushes against the inward crush of gravity, establishing a delicate temporary equilibrium. A star is born. But for the true giants, those destined to become the R136A1s or Stephenson 2-18s of the universe, this birth process is particularly intense. They form in the most turbulent and dense regions of star-forming nebulae, often in massive star clusters where hundreds or thousands of stars are born in close proximity. The terrifying aspect here is the sheer scale of the forces involved even in their creation, gravity, wrestling with unimaginable pressures and temperatures to forge these cosmic titans from primordial chaos. Once fusion ignites, a star enters what's called its main sequence phase. For a star like our Sun, this is a long, stable period lasting about 10 billion years. But for the giants, the story is vastly different. A star 20 times the mass of our Sun might only last on the main sequence for a mere 10 million years. A star like R136A1, with nearly 200 times the Sun's mass, will burn through its core hydrogen in only 2 to 3 million years. That's an incredibly short lifespan on cosmic timescales. Why so short? Their immense mass creates unimaginable pressure and temperature in their cores. This supercharges the nuclear fusion reactions. They burn through their hydrogen fuel at a prodigious, almost insane rate. They are the gas guzzlers of the cosmos, living lives of extreme intensity. The terrifying power here is the sheer rate of energy generation. They are not just bright, they are ferociously, profligately luminous, pouring out energy at a rate that seals their doom. Their brilliance is a death sentence, a countdown timer to their inevitable violent collapse. When a massive star exhausts the hydrogen fuel in its core, gravity begins to win the tug of war. The core contracts and heats up further, eventually becoming hot enough to fuse helium into carbon and oxygen. This new phase of fusion and subsequent fusion of heavier elements causes the star's outer layers to expand enormously, cooling as they do so. The star bloats into a red supergiant, or for the most massive, a red hypergiant, the very stars like Stephenson 2-18 or UY Canis Majoris that hold records for sheer size. This phase is one of terrifying instability. The star is now a colossal, loosely bound ball of gas, its outer layers barely clinging on. They pulsate, sometimes dramatically, shedding vast amounts of material into space through powerful stellar winds or episodic eruptions. VI Canis Majoris, for example, has ejected massive clouds of gas and dust, creating a complex, asymmetric nebula around itself. It's like watching a cosmic pressure cooker on the verge of exploding. The terrifying power is in this visible decay, this shedding of its own skin, a prelude to an even more violent end. The journey through heavier element fusion cannot go on forever. Each stage of fusion provides less energy and lasts for a shorter time. Hydrogen burning might last millions of years, helium burning hundreds of thousands, carbon burning mere centuries, silicon burning, the final stage before the inevitable, might last only a day. Eventually the core of the massive star becomes dominated by iron, and iron is a cosmic dead end. Fusing iron consumes energy rather than releasing it. With no outward radiation pressure to counteract gravity's relentless crush, the iron core collapses in less than a second. This is the moment of ultimate terror for the star. The core, with a mass greater than our sun, shrinks from the size of Earth to the size of a city, triggering a rebound shock wave that tears the rest of the star apart in a Type II supernova, or for the most massive, a hypernova. The energy released is almost beyond comprehension. In a few seconds, the star unleashes more energy than our sun will in its entire 10-billion-year lifetime. This is the terrifying power of stellar death on a grand scale. The explosion blasts heavy elements forged in the star's heart, and during the explosion itself, far out into the cosmos, enriching the interstellar medium from which new stars and planets will eventually form. The very atoms that make up our world and ourselves were once cooked in the hearts of such dying giants. But their death throes are events of unimaginable violence, capable of sterilizing entire regions of a galaxy. For the most massive stars, like R13601, the end might be even more extreme, a hypernova potentially launching devastating gamma-ray bursts, or a direct collapse into a black hole, a silent, final victory for gravity. So, the terrifying power of the biggest stars is inextricably linked to their life cycle. They are born in violence, live brief, furious lives, and die in cataclysms that reshape the cosmos. Their immense size and mass are not just passive attributes. They are the drivers of their accelerated, spectacular, and ultimately terrifying journey from cosmic nursery to cosmic graveyard. We've explored the individual terrors of the universe's largest and most massive stars, their mind-bending scale, their incinerating luminosity, their violent winds, and their cataclysmic deaths. But how do these stellar behemoths stack up against other cosmic phenomena renowned for their terrifying potential? Let's pit them against some of the universe's other heavyweights of horror, including the ever-infamous black hole. Black holes, as we've acknowledged, are the champions of inescapable gravity and the unknown. Their event horizon marks a point of no return, and the singularity at their heart is a mystery that defies physics. The terror of a black hole is often one of stealth and finality, a silent, invisible trap that, once sprung, offers no escape, leading to the bizarre fate of spaghettification or oblivion within the singularity. The biggest stars, however, present a different, more active and visible kind of terror. While a stellar mass black hole might be only a few tens of kilometers across, a star like Stephenson 218 is billions of kilometers in diameter. You don't fall into its event horizon, you're inside it, if you're anywhere within a region that would encompass much of our solar system. Its terrifying power isn't hidden behind an event horizon. It's on full display. Its searing heat, its crushing gravity at its core, though diffuse at its edge, its overwhelming radiation, and its violent ejections of matter. A black hole is a passive predator. A massive unstable star is an active raging inferno. Consider the approach. You might unknowingly drift towards a quiescent black hole until it's too late, but a supergiant star announces its presence from light years away through its sheer luminosity and the stellar winds it expels. The terror is less about a sudden, unexpected trap and more about an overwhelming, unavoidable force of nature. Spaghettification near a stellar mass black hole is a gruesome end, but being vaporized and assimilated into the multi-million-degree plasma of a star that has engulfed your entire solar system is arguably a more encompassing, immediate form of annihilation. When a massive star explodes as a supernova, it leaves behind a spectacular aftermath, a supernova remnant. These are expanding shells of gas and dust, threaded with magnetic fields, and often housing a compact object like a neutron star or pulsar at their core. Supernova remnants are sites of intense particle acceleration and can glow brightly across the electromagnetic spectrum for thousands of years. They are certainly powerful and can be hazardous to nearby environments. However, the terror of a supernova remnant is largely the terror of an echo, the ghost of the cataclysm that created it. The primary destructive event, the supernova itself, is long past. While the remnant is energetic, it is diffuse and expanding. The living, massive star, on the other hand, is a continuous, ongoing source of terrifying power. Its stellar winds are relentless, its radiation output is constant, and the threat of its imminent supernova looms large throughout its short life. A supernova remnant is the aftermath of destruction. A massive star is destruction waiting to happen and actively happening on smaller scales through its winds and radiation every second of its existence. When we look at the energy output of a live massive star compared to a supernova remnant, the difference is staggering. A massive star steadily radiates energy across its lifespan, but when it explodes as a supernova, the energy released in that brief moment can outshine entire galaxies. Over time, the remnant fades, but it leaves behind a pulsar whose beams sweep through space, a stark contrast to the continuous radiation of a live star. Quasars and active galactic nuclei are among the most luminous and energetic objects in the universe. Powered by supermassive black holes, millions to billions of times the Sun's mass, accreting vast amounts of matter at the centers of galaxies, they can outshine their entire host galaxy. Their jets of plasma can stretch for hundreds of thousands of light years, sterilizing anything in their path. On a galactic scale, their power is truly terrifying. However, the terror of the biggest stars is more localized, more personal in a cosmic sense. While an AGN can affect an entire galaxy, it's a phenomenon tied to a supermassive black hole, not an individual star in the same way. The largest stars are individual entities, born from stellar nurseries that live and die within the galactic disk. Their terrifying power is inherent to their nature as stars push to their physical limits. A quasar is the fury of a galactic core. A hypergiant star is the fury of a single, albeit colossal, stellar object. The terror of a star like R136A1 is that it's a star, something we conceptually group with our own sun, yet it possesses power that borders on the output of small galaxies for brief periods during its outbursts or death. Ultimately, each of these cosmic phenomena carries its own brand of terror. But the biggest stars combine sheer, overwhelming physical presence with active, violent processes and a predictably cataclysmic demise. They are not just abstract points of infinite density or fading echoes of past explosions. They are raging incandescent titans that dominate their local space with a terrifying tangible power throughout their relatively brief but spectacular lives. We have journeyed to the very limits of stellar existence, confronting cosmic entities whose scale and power dwarf our everyday comprehension. From the unfathomable volumes of red supergiants like Stephenson 218, capable of swallowing entire solar systems, to the ferocious energy output of mass champions like R136A1 burning millions of times brighter than our sun, the universe showcases its ability to produce true monsters. We've seen how their terrifying power isn't just a passive attribute of their size or mass, it's an active, dynamic force. It's in the incinerating radiation that sterilizes vast swathes of space, the colossal stellar winds that sculpt nebulae and blast matter across galaxies at incredible speeds, and the sheer, unadulterated violence of their inevitable deaths. Supernovae and hypernovae that seed the cosmos with heavy elements but also represent cataclysms of unimaginable destructive force. Even their birth is a titanic struggle of gravity against pressure, forging these behemoths in the most extreme cosmic nurseries. The biggest stars are not just curiosities, they are fundamental to the universe as we know it. They are the universe's high-energy laboratories, pushing physics to its extremes. They forge the heavy elements essential for planets and life. Their explosive deaths trigger new generations of star formation, but this cosmic significance comes at a terrifying price, a life lived on the edge, furiously burning through fuel, destined for a spectacular and violent end that can reshape entire galactic neighborhoods. So what is the ultimate takeaway from confronting the terrifying power of the biggest stars ever found? It is perhaps a profound sense of awe mixed with a healthy dose of cosmic humility. These stars remind us that the universe is not always a serene, peaceful expanse. It is a place of extremes, of creation and destruction on scales that defy easy imagination. The power locked within a single one of these stellar titans is enough to make all human endeavors, all our worldly concerns, seem infinitesimally small. They are a testament to the raw, untamed forces that govern the cosmos. Their terrifying power is not malevolent, but a natural consequence of the laws of physics, operating at scales we rarely encounter. Understanding them helps us understand not just the life cycle of stars, but the very evolution of the universe itself. They are the ultimate cosmic fireworks, beautiful and terrifying in equal measure, reminding us of the dynamic and often violent nature of the universe we inhabit. What aspect of these colossal stars do you find most terrifying or most awe-inspiring? Which stellar giant captures your imagination the most? Share your thoughts and cosmic ponderings in the comments below. We're always fascinated to hear your perspectives. If this journey to the edge of stellar existence has expanded your cosmic horizons, please give this video a thumbs up and don't forget to subscribe to The Insane for more explorations into the deepest wonders and most terrifying truths of our universe. Thank you for watching, and as always, keep looking up.